We are moving forward to the quarterfinals of the 2025 MIT Integration Bee, and today's focus will be on quarterfinals number 1, where the first problem was the definite integral from x equals to 1 to x tending to infinity of x to the power 5 times e to the power negative x. Problem number 2, which is actually very complicated, was the integral from x equals to 0 to x equals to 100 of, open bracket, the ceiling function of x minus 1 over 3 minus the floor function of x plus 1 over 3, close bracket, times x ceiling function of x minus 1 over 5 minus the floor function of x plus 1 over 5, close bracket, times x minus 1 over 7, ceiling function, minus the floor function of x plus 1 over 7, close bracket. Problem number 3, this is actually an easier one. Indefinite integral of x squared over the square root of 4 times e to the power 2x plus x squared plus 2x plus 2 or squared. And then there were tiebreaker problems. Problem number 1, the definite integral from x equals negative 2024 to x equals 2026 of x, open bracket, 1 plus cosine of x minus 1 over 2025 times pi, close bracket. Problem number 2 under the tiebreaker set of problems, the definite integral from x equals to 0 to 2 of the floor function of v to the x. And problem number 3, the definite integral from x equals to 0 to x equals to 225 of the floor function of x over the ceiling function of square root of x. Actually, a very interesting problem. And then there was a lightning round, and the only problem under the lightning round was the indefinite integral of the arctangent of x minus x times the arctangent of x all over 1 minus x plus x squared minus x to the power 3. So these are very interesting problems, and we're going to try and solve them one by one. Hope you do enjoy them. So for the first problem, this is actually interesting. I think it just tests on knowledge of integration by parts. So we do have a definite integral from x equals to 1 to x tending to infinity of x to the power 5 times e to the power negative x. So this can be expressed as the same integral, but the e to the power negative x can be expressed as the derivative of negative e to the power negative x. And that is for the reasons that are obvious. So using integration by parts, when you have a product of two functions, one v and one the derivative of function u, when integrated, you have uv minus the integral of the function u now and the derivative of function v, which is dv. So our u is negative e to the power negative x, and our v is x to the power 5. Therefore, the first integral there now becomes negative x to the power 5 e to the power negative x with the limits applied appropriately. Now this is important if one needs to find the limit for when x tends to infinity here. This could be expressed as x to the power 5 over e to the power x, and since both the numerator and denominator tend to infinity, we can use L'Hopital's rule, and we can keep differentiating until a point where the numerator x to the 5 goes all the way to 1, and obviously the denominator consistently remains e to the x. And so that tells you that we have 1 over infinity, 1 over an item that tends to infinity, and that means that the expression goes to 0. Anyway, focusing on the second part here, v being x to the 5, derivative of x to the 5 is what we have as dv here. And so just back to what I had alluded previously, the limit for x tending to infinity for this part would this would be 0. X tending to 1 will be minus 1 over e, and so we have 1 over e remaining there. And obviously this minus and minus multiplying with one another becomes a positive, so we have a plus. The derivative of x to the 5 is 5x to the 4, so we have 5 here. And we have quite a similar integral to what we had previously here, but the x term the degree of the x term has decreased to 4. So we can keep continuing with the process, but it's now easy to use the same concept that we use for the x to the 5 to the 4, and so we'll just continue 1 over e plus 5, 1 over e. Now we have 4 here, but now this has gone to 3, and we keep continuing on that. So we have 1 over e plus 4, 1 over e, and now we have 3 inside this bracket, and just keep continuing. And we see a pattern that we've exploited very adroitly. So let's keep going, and then we've reached to a point where we now have 1 here and there's no x, but that can be integrated now to negative e to the x with the limits applied appropriately. So when you apply these limits, when x tends to infinity for negative e to the power x, that is 0, minus x tending to 1 of e to the power x, that is obviously 1 over e. I apologize, this is not, we forgot a negative here, but we can see that this obviously will be 1 over e. Yes, there. And so we can now unwrap the brackets, and so we have 1 over e, 5 over e, 5 times 4 over e, plus 5 times 4 times 3 over e, plus 5 times 4 times 3 times 2 over e, plus 5 times 4 times 3 times 2 times 1 over e. And so this 2 here in the numerator, we get 120, and here we have 60, and here we have 20, here we have 5 and 1. So we can now just add things up, and so this is 240 plus 6 is 300, 320, 325, 326. So that becomes 326 over e, and that's the answer that was being sought for. So on to problem number 2. This problem is a fairly intricate problem. I would like to go very slowly explaining how we arrive at the answer, okay? So we have the integral from x equals to 0 to 100 of the product of, as we mentioned, the ceiling function of x minus 1 over 3 minus the floor function of x plus 1 over 3. And that is repeated for x minus 1 over 5, x plus 1 over 5, x minus 1 over 7, x plus 1 over 7. So I think it's good to remind ourselves what a floor function is and what a ceiling function is. First, for the ceiling function of fx means that equals to k plus 1 when fx is greater than k or less or equal to k plus 1. And the floor function of fx is equals to k when fx is greater or equal to k or less than k plus 1. So focusing on x minus 1 over 3 ceiling function, that is equals to k plus 1, and that means that that happens when x minus 1 over 3 is greater than k or less or equal to k plus 1. We multiply both sides by 3, that's a positive constant, and so the inequality signs remain. And then you can add both sides by 1 since we're adding positive integer or number. The inequality signs remain. So we do have a scenario where x minus 1 over 3 ceiling function is equals to k plus 1 when x is between 3k plus 1 and 3 times 3k plus 1 plus 1. And then the floor function of x plus 1 over 3 equals to k when x plus 1 over 3 is greater or equal to k and less than k plus 1. So that means that 3k x plus 1 greater or equal to k, 3k, or less than 3 times k plus 1. And when we subtract 1 from both sides, this expression here is equals to k when x is between 3k minus 1 and 3 times 3k plus 1 minus 1. To put this in a more graphical sense, so if we have 3k here and we have 3k plus 1, 3 units ahead, so we're just adding 3 points ahead, and then on the vertical axis we have k and k plus 1. It means that for the ceiling function of x minus 1 over 3, it is equal to k, and you note there's an open circle here. It means at this point the value is k minus 1, but we see that it is equal to k. The ceiling function is equals to k between 3 times k minus 1 plus 1 all the way up to 3k plus 1. And then it transitions to k plus 1 from 3k plus 1, right? And this happens to be like that until 3k plus 1 plus 1. However, for the floor function, the scenario is different. From this expression, as you can see, 3k minus 1 is here, and we see greater or equal, so we have a filled circle here. This stretches all the way up to 3k plus 1 minus 1, which is here, and then it transitions now to k plus 1. But now you see we are looking for the difference, right? We are looking for the difference between these two functions. The difference only happens in this point here, this domain. That is 3k plus 1 to 3 times 3k plus 1 minus 1. So in this interval is when the blue minus green becomes 1. So blue minus green equals to 1. Right? So in this region here is when this function becomes 1. So we say that the ceiling function of x minus 1 over 3 minus the floor function of x plus 1 over 3 equals to 1 when x is greater, and as you can see here, greater than 3k plus 1 and less or equal to 3k plus 1 minus 1. 3 times k plus 1 minus 1. So we can use the same kind of thinking and say, okay, for the first item, this is what we have. For the ceiling function of x minus 1 over 5 minus x plus 1 over 5, that equals to 1. just using the same thinking we use for 3k plus 1. So it is when we have 5k plus 1, x greater than 5k plus 1, and less or equal to 5 times k plus 1 minus 1. And for 7 in the denominator, we use the same expression, right? So the product now happens when there's an intersection of all these functions. When all these things equal to 1 is when this product equals to 1. Otherwise, if any of this becomes 0 at any interval, that thing just collapses to 0. So we have to now look for regions of intersection, and we know that the span for this is a span of 1. In other words, from 3k plus 1 to 3k, 3 times k plus 1 minus 1. The difference there is just 1. So let's go ahead and draw a table and investigate this. I know this is intimidating, but I've decided to split x because we're looking from x equals to I think it's 0 to 100. So let's just split between 1 to 10. So the difference here is between 3k plus 1 and 3 times k plus 1 minus 1. So in other words, when k is equal to 0, it's 1 when we have 1 to 2. In other words, when k is 0, we have 1. And when k plus 1 becomes, when k is 0 and k plus 1 becomes 1, so 3 times 1 minus 1 is 2. So the interval is 1 to 2. And then we have 4 to 5. And then we have 7 to 8. That is when this guy is 1. And then between 10 and 20, it is 10 to 11, 13 to 14, 16 to 17, and so on. And then we did the same for 5k plus 1 to 5 times k plus 1 minus 1. And these are the regions when this value is 1. And for 7k to 7 times k plus 1 minus 1, these are the regions of interest. So where is the region of intersection here? We can only see that it only intersects between 1 and 2, because 4 to 5 falls right between here, and then 7 to 8 falls right between here. So the only valid region of intersection is 1 to 2, and so we have only one region here. And then here again, 10 to 11 happens to be the only region of intersection, because 13 to 14 would fall right between here, and 16 to 17 would fall right between here as well. 19 to 20 would fall after this. So the only region of intersection is 1, and that is 10 to 11. Right here, the only region of intersection happens to be 22 to 23. And then 25 to 26 falls right between here. So there is a 0 for this region somewhere. And 28 to 29 happens to be right here. So this is the only region. So we have only one area of intersection. Here we do have two regions of intersection. 31 to 32 is okay. It falls between here and falls between here. 34 to 35 falls between here, so this we can ignore. 37 to 38 falls here, but also falls here. So we have two regions of intersection. And we can continue like that until now, when we sum up the regions of intersection, they all come to 14. Mark you, between 90 and 100, there is no region of intersection. So the sum of all points, of all intervals that have a 1 that is consistent across this and this and this are 14. And as we know, the x extent for those domains for the first expression here is only 1. So the area is going to be equal to all these 14 intervals times the x extent, which is 1. So the integral now means that we have 14 as our answer. So that is how you may be able to solve that problem. It's actually pretty intricate, but also nice and nifty. Problem number 3, the indefinite integral of x squared over the square root of 4e to the 2x plus the square of x squared plus 2x plus 2. So the first thing is I would want to pull out the 4 to the times e to the 2x out. So we get 2 times e to the x in the denominator and the square root of 1 plus, now this goes under this and we have x squared plus 2x plus 2 over 2ex. And then we can say let whatever is under the bracket here be equal to the hyperbolic sine of u, and that means that the derivative with respect to x on both, with respect to u, sorry, on both sides, we have the derivative of the numerator, keeping the denominator, minus or plus the derivative of 1 over 2ex, which becomes negative 1 2ex, and the numerator remains. So this times dx du, and then when you simplify it, the 2x and 2 here cancel each other, and we have left with negative x squared over 2ex times dx du being equal to cos u. So derivative of sin u with respect to u is going to be equal to cos u. And so x squared over 2ex dx, and this is what we have here, times obviously dx here, can be substituted off by negative cos u du. So we now substitute things. We have negative cos u du over 1, the square root of 1 plus sin u squared, since we had substituted this with sin u. So the denominator becomes cos u squared, which is the same as cos u, since we're getting the square root, and the cos u's both in the numerator and denominator cancel out, and so that becomes the negative integral of 1, and so our answer is u. But since we had said that this expression here, x squared plus 2x plus 2 over 2ex equals to sinh u, then it means that u is equal to the arc sinh of x squared plus 2x plus 2 over 2ex. And we can plug that in, and so our integral of x squared over the square root of 4e to the 2x plus the square of x squared plus 2x plus 2 is negative arc sinh of x squared plus 2x plus 2 over 2e to the x plus the integration constant. So on to the tiebreakers. The first problem obviously looks pretty intimidating, but it is actually a very simple problem, and I think it pegs on substituting for the x minus 1 over 2025 times pi with a simpler expression as u. So let's say let u be equal to that, and that means that du dx is equals to pi over 2025, and that means that 2025 over pi du is equals to dx. And also from here we can see x now is equals to 2025 over pi u plus 1, meaning that now we can now change from the x domain to the u domain. Mark u, when x is equals to negative 2025, we have negative 2024 minus 1 over 2025, which is going to be negative 2025 over 2025 times pi, which is going to be negative pi. And the same thing happens for the upper domain, and so u is the integral from u equals to, and in the u domain we're going to have an integral from u equals to negative pi to u equals to pi of, in place of x here we have this expression here, which is 2025 over pi u plus 1 times 1 plus we had substituted everything under the cosine with u, and then dx becomes 2025 over pi du. And so we can pull that constant out, and we have now 2025 squared over pi squared, the integral of u plus cosine u cosine u, and then with this we have only 2025 over pi integral of 1 plus cosine u. And so we can use, we could go as well ahead and express cosine u as a derivative of sine u, and we can now use integration by parts here, which means that we have a product of v and a derivative of function u. Integrated, we have uv minus the integral of the product of u and the derivative of v. So that means we have 2025 squared over pi squared times the integral of u, which is u squared over 2. The limits, obviously, negative pi and pi, plus the same constant here times uv is u times sine u, with the limits applied appropriately, minus here the same constant sine u times integral from u equals to pi over negative pi to pi of sine u times the derivative of u. And then 1 plus cosine u can be integrated to u plus sine u, and the constant here is the same constant here. This becomes obviously pi squared over 2 minus negative pi squared, which is pi squared over u. So this becomes 0. And the same thing here, pi sine pi minus negative pi sine negative pi. Sine pi is 0, sine of negative pi is 0. So this thing also goes to 0. Minus 2025 squared over pi squared, the integral of sine u, plus u with the limits applied is pi minus pi, so this becomes 2 pi times 2025 over pi, and then we have sine pi minus sine negative pi. This is 0, this is 0, so we're left with this integral here plus 2025 over pi times 2 pi. Okay, then the integral of this guy is negative cosine u, which becomes negative of cosine pi minus cosine of negative pi. Cosine pi is negative 1, cosine negative pi is also negative 1, so negative 1 minus negative 1, this becomes 0. So our answer becomes 4050. And that was what was being looked for. Okay. So the integral from x equals to negative 2024 to x equals to 2026 of x times 1 plus cosine of x minus 1 over 2025 times pi, is 4050. So another interesting problem, the definite integral from x equals to 0 to x equals to 2 of the floor function of e to the x. So going back to the definition of the floor function of fx being equal to k when fx is greater or equal to k and less than k plus 1. So what is, first of all, let's think about the upper limits. So we know the lower limit is going to be 1, e to the 0 is 1, e to the 2 is 7.389. Now for floor function of e to the x being equal to k, that means that that happens when e to the x is greater or equal to k or less than k plus 1, taking the natural log of both limits. So we have log k, x will be greater than or equal to log k and less than the natural log of k plus 1. So our integral here now will be interesting because now we'll begin from 1 because that's where e starts. E to the 0 is 1. So k is equals to 1 to 6 of this interval. So we're beginning with log k to log k plus 1, and in this interval this value is just k plus, since after 6 now we are going to have 7, and that only happens from the upper limit 2 to log 7, log of 6 plus 1, which is log of 7. So to make it very clear, so if we have our function and this is 2, it means that we are having the floor function is there up to log so we're beginning from to log 1, not log 1 but log 2 rather, then it transitions up here, so this is 1, and then it goes to just 2 all the way up to log 3, and then it becomes 3 all the way up to log 4, and this process goes on until now it becomes 6 here, and this goes on up to log 7. Right? But now this difference between, let me just extend, this is a little bit exaggerated. So this area here, we don't know the upper limit. The upper limit is 2, but we need to know this area here. So this is 7, obviously. The height is 7, but the width now is going to be 2 minus log 7. And that's why we have brought this component here. And then for the rest, we're just summing up the strips. There k, for example, k is equals to 1, k is equals to 2, k equals to 3, and so on, with the x, the width in the x side, on the x side being equal to log k plus 1 minus log k. So when we integrate things there, we get x. We actually even didn't need to do the integration. Would just have considered these as rectangles. But anyway, doing our due diligence is fine. So we have x times k, and we're applying the limits. So that becomes k times log k plus 1 minus log k. And then obviously 7 times 2 is 14 minus 7 log 7. So summing up from k equals to 1 to 6 of k times log k plus 1 over k. And this can be expressed as log of 2, because we have 1 times 1 plus 2 over 1, so it becomes log 2, and then log 2 times, 2 times log 3 over 2 plus 3 times log 4 over 3 times 4, all the way up to 6 times log 7 over 6. And using the rules of logarithm, that means we're multiplying whatever we have here, but the powers now have to go up. So we have 2 times 3 over 2 as log 2 times 4 over 3 times 3, to the power 3, and this is under the log function, 5 over 4 to the 4th, and all the way up to 7 times over 6 to the 6th. As you can see, the 3's, this 2 and 2 will cancel with 1, 2, and we're left with 1 over 2 here. And then 3 and this 3 will cancel, and we're left with 1 over 3. This 4 and this 4 will interact, and we're left with 1 over 4. And this propagates until we have natural logarithm of 1 over 2 times 1 over 3 times 1 over 4 times all the way up to 7 to the 6 over 6. Now we can pull this guy back here because negative 7 log 7 is the same as log of 1 over 7 to the 7, right? And we can pull this back here so that now we're multiplying everything under the log function. And as you can see, that interacts very well, because then we're left with 1 over 7. And so that means we have this 14 minus, because now these fractions now can go, we can get the reciprocal of the factorial of these numbers of 7. So we have 14 minus the natural logarithm of 7 factorial, which is 14 minus natural logarithm of 5040. And that's the answer that we're looking for. The integral from x equals to 0 to 2 of the floor function of e to the x is 14 times the natural logarithm of 5040. Okay. So this is actually a very interesting problem. I found this to be the most interesting of all. The definite integral from x equals to 0 to 2025 of the floor function of x over the ceiling function of square root of x. So let's begin with the definition of what a floor function is. The floor function of fx equals to k when fx is greater or equal to k and less than k plus 1. For the ceiling function, it's equals to k plus 1 for x when fx is greater than k or less or equal to k plus 1. That means that for x, floor function is equals to k when x is between this domain. What about for the ceiling function of the square root of fx of x? Sorry, it's equals to k plus 1 when they so when x square root of x is greater than k and less or equal to k plus 1. What that means is that it happens when the square, when x is greater than k squared and less or equal to k plus 1 squared. So what does that mean? That means that we do have that as our summary, right? So if we have the x-axis 0 all the way to 2025, and the y-axis are shown here, for the floor function of x, it's just going to be equal to those steps, right? So that between 0 and 1, it's 0. And between 1 and 2, it transitions now. It is 1. Between 2 and 3, it's, the floor function of x, is it's just 2 for the entire duration. And then that happens all the way. So it's just, these are, whatever you have in the x is what you see in the y, but the transitions happens when now x transitions to 1, so it moves to 1 and so on. What about the blue function being the ceiling function of the square root of x? Between 0 and 1, because we're looking at that being equal to k plus 1, so it's going to be equal to 1. Between now 1 and 4, it's going to be equal to 2, because now the square root of all these numbers is going to exist between 1 and 2, and so the ceiling is the integer, the upper integer, so that is going to be, it's going to be equal to 2. Between 4 and 9, the values, the square root of values here are going to be between 2 and 3, so the ceiling becomes 3. And so that is what we're going to be contending. So now transitioning to putting this into some analytical light, we have the integral from x equals to 0 to 2025, and as you can see, the square root of this value, especially the ceiling, means that now we're going to be moving from 1 to 45, which is the square root of 2025. So let's say we have L equals to 1 to 2025 square root, and then the denominator is 1 over L, because we have 1, 2, 3 up to 45. But between L is equals to 1 to L is equals to 2, we have so many things in the numerator. So we are summing from k equals to L minus 1 squared to L squared minus 1. The example would be if when L equals to 2, 1 over 2 is the denominator, and then we're summing between L minus 1 squared, so 2 minus 1 squared is going to be equals to 1, and then there's obviously equal to 2, 3, 4, all the way up to 2 squared minus 1, which is 3, before now it transitions to 4. Because when L is equals to 3, then we have 1 over 3 times 3 minus 1 is going to be equal to 2, so it's 4, 5, 6, 7, up to 3 squared minus 1, which is 8, and then transitions to 9 in the next cycle. So knowing our arithmetic progression, when you're summing from k equals to 1 to n, the sum is n times n plus 1 over 2. So what we're doing is we are summing all the way up to this top value, and then subtracting the sum up to this part. But we have to be cognizant that now we have to add back this initial item. So we have 1 over L times the sum to the upper part is going to be L squared minus 1 times n plus 1 is L squared minus 1 plus 1 over 2 minus n here is L minus 1 squared, so L minus 1 squared times L minus 1 squared plus 1 over 2 plus the initial term here, L minus 1 squared. So we have the summation from L is equals to 1 to 45 of 1 over L. L minus 1 plus 1 is just L squared now. And then what we're doing is we just have this repeated. So multiply the L squared across, we have L to the fourth minus L squared minus expanding things. So we have L minus 1 to the power 4 plus L minus 1 squared. And then just adding this as normal. So we'll expand L minus 1 to the fourth, which is going to be so L to the fourth minus 4L to the 3 plus 6L squared minus 4L plus 1. And then expanding L minus 1, this L squared minus 2L plus 1. Let's keep this as it is right now. Came up to there. Now, going forth is L to the fourth and this L to the fourth interact, so that goes to 0. So let's see, we are left with now minus minus, so 4L to the cube, this L squared term here, combined we have minus 8L squared plus this L term becomes plus 6L minus 2. Obviously divided by 2, we've expanded this to L squared minus 2L plus 1. So we divide this by 2, we get 1 over L times, we have 2L cubed minus 4L squared plus 3L minus 1. And then when you add this, the constant cancels out. And then 3L minus 2L, we get just 1L. And then minus 4L squared plus L squared, we have minus 3L. So 1 over L times 2L cubed minus 3L squared plus L. When we divide everything here with L, we get the summation from L is equals to 1 to 45 of 2L squared minus 3L plus 1. And now using back to this arithmetic progression, when we're summing the k term, we have n times 1 over 2. When we're summing the k squared, we get n times n plus 1 times 2n plus 1 over 6. So using these formulas, upper limit being 45, lower limit being 1, we have twice. N is 45, so 45 times 45 plus 1 times 2 times 45 plus 1, which is shown here, minus 3. Using this, we have 45 times 45 plus 1 over 2, plus, we're just adding ones, 45 times, we have 45 here. So 2 divided by 3, so by 2 here is 1, by 2 here is 3, 45 by 3 is 15 here. So 15 times 46 times 91 minus 3 times 2 by 46 is 20. 46 by 2 is 23. So we have 3 times 45 times 23 plus 45. So multiplying this, we get 62,790 minus 3,105 plus 45. That brings us to 59,730, and that was the answer that was being sought for. So our integral from x equals to 0 to 2025 of the floor function of x over the ceiling function of square root of x is 59,730. Certainly a very interesting problem. On to the lightning round. This was a simple problem actually. I think it just required 1 minute for somebody to solve this. So what we're going to do is we're going to factorize. We're going to pull out arctangent of x. So we're left with arctangent of x plus 1 minus x. And then in the denominator we have 1 minus x plus x squared 1 minus x. Divide both the numerator with 1 minus x. We are left with arctangent of x over 1 plus x squared. And that means we have arctangent now of x times the derivative of 1 over x squared is derivative of arctangent of x. We can use integration by parts, but also it's very obvious to see here that when you have such an expression, it's the same as the derivative of a half, the square of whatever is under the derivative function there. So that integrated, you get half times the arctangent, that times the square of the arctangent of x plus the integration constant. And that is the answer that was being sought for. So we've gone through these problems on the quarterfinals, number 1 of the 2025 Integration Bee at the MIT Massachusetts Institute of Technology. These are very interesting problems. Our goal here really is not to power through the problems like we're in a competition, but really to break the concepts down so that you could follow, and then maybe because a lot of the steps here could be abbreviated and you could move through them so fast. But we wanted to explain the thinking and the logic and the progression of things as you go on solving them. So if you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. If you haven't liked, please like our video. If you can, please share. We do enjoy mathematics. If you have solutions that you think are better than what we propose, we welcome those suggestions. We will make videos based on those suggestions because we do respect your thought on this as well. So until next time, have a wonderful time, be blessed, and yeah, thank you.